Hey guys, my name is IBM, and I think this is going to be the last. It's going to be the last lesson for nuclear physics. I'm trying to go through nuclear physics as one of the paper four topics or as one of the early topics. Don't forget, this is AS physics, and this is physics. Physics is the topic as we take. It is actually going to be paper four. We are dealing with the nuclear physics, but remember the course outline for A level. It includes circular motion, rotation, ideal gases, temperature, thermodynamics, simple motion, oscillations, electric fields, magnetic fields and electromagnetic induction, capacitancy, alternating current, nuclear physics, quantum physics, astrophysics, medical physics, and do not forget nuclear we are finishing nuclear physics. So we are finishing nuclear physics. This is A-level physics 9702 paper 4. I think this is nuclear physics lesson 4. And I think this is going to be the last unit. If you're a teacher, you can teach nuclear physics in only 4, I think in 4 hours if you are slow. Nuclear physics should be taught in 4 hours. That is, it shouldn't take more than a week if you are really slow. But 4 hours are enough to finish nuclear physics, and students should be able to practice and go through the solved past paper questions to be able to gain a lot of confidence. Okay, so in lesson 4, we shall go to the last part of nuclear physics. Remember, I said nuclear physics has 3 major parts where we discuss the mass excess or the mass defect. We discussed binding energy, and the last part is going to be radioactive decay or radioactivity to be specific. I want you to recall that some elements with unstable nuclei emit particles and or electromagnetic radiation in order to become stable. This is what you call radioactivity, I think, in particle physics, last topic in AS. You mentioned that some nuclei were able to emit alpha, beta, and gamma radiations spontaneously in AS physics, particle physics. So those nuclei which were able to emit alpha, beta, and gamma radiations were said to be radioactive, and they were at times called radioisotopes. Why were they called radioisotopes? Remember, isotopes are atoms which have the same number of protons but different number of neutrons, resulting into different nucleon numbers. The isotopes have the same proton number but different uh, neutron number, which gives different nucleon number. So what is radioactivity, or what do we mean by radioactive decay? So in particle physics, you must have mentioned spontaneous and random, but it was illegal to mention spontaneous and random at AS level. However, we know that any unstable nucleus is most likely going to disintegrate either on its own. Apart from nuclear fission, it may disintegrate on its own to emit alpha, beta, or gamma radiation. Sometimes neutrons accompany such processes. So, in such a process, where the decay is not induced by a neutron, as we saw with the nuclear fusion, with the nuclear fission, it is most likely going to be called radioactive decay or radioactivity. So what do we mean by radioactive decay or radioactivity? So radioactivity or radioactive decay is going to be defined as the spontaneous, I think I should use black, the spontaneous and random disintegration of a heavy unstable nucleus into more stable nuclei with lower total mass through the emissions of alpha, beta, and gamma radiations. Sorry about this. So radioactivity is actually resulting into the emission of alpha, beta, and gamma radiations. The process is spontaneous. The process is random, and it is accompanied by the emission of alpha, beta, or gamma radiations. Sometimes two of them are emitted, sometimes one of them is emitted, or sometimes all of them could be emitted. An alpha particle could be emitted, a beta particle could be emitted, and sometimes energy also accompanies such reactions. So such a reaction is said to be, such a decay is said to be radioactivity. Now, to distinguish this from nuclear fission, where a heavy nucleus was decaying by emission of by a heavy nucleus was decaying into two lighter nuclei accompanied by emission of energy. Here, a heavy nucleus is decaying into, it could decay into one lighter nucleus or one stable nucleus by emission of alpha, beta, or gamma radiations. In radioactive decay, we are not using a neutron. The nucleus is decaying on its own. That's why we are going to call it spontaneous. Let's understand the meaning of these two terms, spontaneous and random. Let's begin by understanding the meaning of spontaneous and random nature. Radioactivity is going to be defined as being spontaneous. What we mean by something being spontaneous? It is going to be considered spontaneous because it is not affected by any external factors. Nothing in the environment influences radioactive decay. We are not inducing it using a neutron. We are not heating. We are not applying any chemical catalyst. We are not changing the pressure of the surrounding. So the decay is said to be spontaneous. It comes from within the nucleus. Nothing in the environment influences or stops radioactivity. So we say it is not affected by external factors such as temperature, pressure, or chemical catalysts. Therefore, we say radioactive decay or radioactivity is spontaneous. On the other hand, radioactivity could be defined as being random. What do we mean by radioactivity being random? A random process is one in which we cannot predict the outcome. For example, if you toss a coin upwards, if a coin has a head and a tail, you are sure that in one toss you could get a tail or you could get a head, but the probability of getting a tail or a head is going to be 1/2. If you toss a die, you know that in one toss you could get a 5, a 1, a 3, but you are not sure what exactly you are going to get when you toss the die once. So it is just a probability, which in this case could be 1/6. So radioactivity is like that. It is really random. We could have a sample having several nuclei, but we cannot pick out which nucleus is going to decay next. Therefore, we say radioactivity is random. So, if a dice is thrown simultaneously, we are sure that it is likely to show a 1, a 2, a 3, a 4, a 5, a 6 in one throw, but cannot show all of them at the same time. And we cannot predict what exactly it is going to show in one throw. So we say this is a random event. And if you're a mathematician, if 12 dice, if 12 die are thrown, if 12 die are thrown, it is likely that two will show a 6, and so on. If 18 die are thrown, there is a likelihood that 3 of them will show a 6, and so on and so forth. But it's not possible to predict the likely number of sixes that will be thrown. But it is possible to predict that if we have 12 die, 2 of them are most likely going to show a 6. So it is possible to predict the likely number of sixes that will be thrown, but impossible to tell which of the die out of the 12, which of the die is going to show a 6 when you throw them at the same time. So we therefore describe the situation as the situation by saying that that the throwing of a 6 is a random process, or it is actually a random event. So the meaning of the word random in this context is that we cannot predict which nucleus will decay next in a given sample in relation to throwing a die. So that is the meaning of the terms spontaneous and spontaneous and random. We now know for spontaneous, nothing in the environment influences the radioactivity to occur. And then for random, we know that we cannot predict which nucleus in a given sample is most likely going to decay next. So how do we determine radioactivity, or how do we measure radioactive decay? So to measure radioactive decay, we are going to use, or we must have used, you must have mentioned the GM tube in particle physics, even though it was illegal to mention. So Mass, Geiger and Muller were able to come up with a simpler way of determining radioactivity. We just want to know the rate at which nuclei in a given sample are actually disintegrating. That is what we are calling the activity. Or we just want to know how many, or the count rate at which nuclei in a given sample are decaying or are disintegrating. That is what we call the activity, and this is measured using what we call a GM tube or a Geiger-Müller tube. So Geiger and Marsden were able to come up with this simple apparatus. This is a simplified apparatus that you may not really need to draw in an exam. But of course, in paper 5, you may need to have an idea of the GM tube. So the GM tube may look like this, and we shall use the GM tube or the Geiger-Müller tube connected to a retimeter, as shown in this diagram. And the retimeter is going to tell us the count rate of the radioactive decay. It will give us a count as several nuclei in a given sample here disintegrate. They will emit particles. They will either emit alpha, beta, or gamma radiation, and these are going to be picked by the GM tube. Now, the GM tube, even though I'm not supposed to give you details of how it operates, the GM tube uses ionization to detect these particles. So if an alpha particle enters the GM tube, it causes ionization, and it will affect the count rate. If a beta particle enters the GM tube, it causes ionization and to affect the count rate. Unfortunately, if a particle emits a gamma radiation, remember gamma radiations have no charge, so they are the least ionizing, almost not ionizing, so the count rate is not going to be affected. So the GM tube is not a good method for determining the count rate or the radioactivity, because gamma radiations are most likely not going to be detected since they are not actually ionizing. So radioactive decay can be measured with a GM tube connected to a retimeter. So this is a retimeter. The retimeter measures the count rate of the radioactive decay by just registering the rate of ionization taking place in the GM tube. So that is how a GM tube operates. You may not need a GM tube for paper 4, but you may need an idea of the GM tube for paper 5, which is planning, analysis, and evaluation. One important thing we need to note about the GM tube is that even when there is we remove the source, even when we remove the source of radiations, the GM tube will never show a zero reading. Even without the source, even if we don't have a source of radiations here placed, the GM tube or the count rate, the counter will always show a certain value. It may never point to zero. Why? It means even if we have removed the source here, we don't have a source here, it is still giving a reading, which means there are certain radiations which are existing in the environment. And these radiations, your teacher must have told you that these are background radiations, that is in IGCSE, in the nuclear physics or particle physics of IGCSE. Even in the absence of this source that we have placed in front of the GM tube, the counter may still give a reading, or the retimeter may still give a reading, which means it is registering some radiations in the environment. And these radiations, your teacher must have called them background radiations. So, a few things we need to note here include the following. Number one, a radiation detector can register a count rate of 20 to 50 counts per second, even in the apparent absence of radioactive materials. Even in the absence of radioactive materials, the counter will give the retimeter will give some count. Why is it giving some count? We say this is what we call the background radiations. Where do these radiations come from? Astronomers believe that during the formation of the Big Bang, there are remains of the Big Bang which exist in the universe, and these are in all parts of the universe and can continuously be detected by any detector of radiations. These radiations could come from underground, from the atmosphere. They could be considered to be cosmic rays arriving at the Earth's surface. So these contribute to what we call background radiations, or they give us what we call the background count. The other thing we need to note include, we should also note that the count rate measured by the GM tube could be lower than or higher than the activity of the sample for several reasons. Remember, I mentioned there exist radiations in the environment, which even in the absence of radioactive material next to the detector gives a reading. Also note that the detector uses ionization, and ionization relies on charge. So for emission of gamma radiations which are not ionizing, it means the count rate is affected. So that's why we are saying the count rate measured by the GM tube could be lower than or higher than the actual activity or the actual count of the sample or the actual radioactivity of the sample for the following reasons. The first one, and the most obvious one, I've mentioned it as background radiation. Background radiation from cosmic rays arriving from the atmosphere. These ones could make the detected activity to be higher than the actual one, because if the sample is emitting gamma radiations, I mean it is emitting an alpha particle or alpha particles, and again there exist other alpha particles existing in the environment which are moving towards the detector, that means the registered count rate is going to be higher than expected. The registered count rate of a sample is higher than what is expected. Number two, I said that gamma radiations are not always detected. Reason, because they are weakly ionizing, they're almost not ionizing. Whenever they are not detected, it means the detector or the counter is giving an output, or is giving a rate or a count which is actually less than the normal count of the sample. Because the sample is decaying by emitting gamma radiations, which are not causing ionization in the GM tube, such a count or such a decay is not, or such an activity is not registered. So that means what is observed, the count rate observed on the radiometer is going to be less than normal. Number three, sometimes there is what we call self-absorption. Imagine an alpha particle is emitted and is absorbed within the sample. That's what we call self-absorption. Some radiations are absorbed within the same sample before reaching the detector. Before reaching the detector, making the activity to be lower. So some radiations are absorbed within the sample before reaching the detector, making the detected activity lower. So that is one other reason as to why the activity may not be exact. There is what we call self-absorption. Radiations emitted are absorbed within the sample before reaching the GM tube. That means such radiations will not cause ionization for the count for the activity to be registered. Number 4, the detector is normally unidirectional. Remember, radioactivity is random, which means the particles emitted can be emitted in any direction. But because the detector is just unidirectional, it only detects radiations which are coming towards it. If an alpha particle is emitted in a different direction from the detector, such an alpha particle is not going to be detected. So the detector is unidirectional, yet radioactivity is random in nature, and so some radiation will move away from the detector rather than towards. Of course, if those radiations are not detected, it means the registered activity is going to be lower. Number 5. Sometimes the daughter nuclei may also be radioactive. Of course, this one increases the activity. Imagine, uh, imagine uranium gives us, let's say, barium, and barium is also radioactive. If uranium gives us barium plus an alpha particle, yet barium is also active, barium also immediately emits another nucleus, say Kr plus maybe beta. So barium was the daughter nucleus for our sample, which was uranium. But barium was also very radioactive. It also disintegrated to emit another particle. So that means an alpha particle is going to cause ionization, and the beta particle will also cause ionization, which makes the activity to be higher than normal. So the daughter nuclei may also be radioactive. This increases the activity, which it makes the activity to be higher than normal. And lastly, maybe sometimes there could be a dead time, or the counter could be inefficient, and this could affect the activity. So those are the reasons as to why the activity or the measured count rate could be higher or lower. Later on, we shall use the term half-life to refer to the same thing. Either the activity or the half-life could be higher or lower than what is expected. So these are the reasons as to why the activity could be affected. I mentioned background radiations, gamma rays not being detected, self-absorption, the detector being unidirectional, daughter nuclei being radioactive. We have what we call dead time of the counter, or the counter being inefficient. Those are those are some of the reasons as to why the activity or the count rate registered by the device may not be exactly correct. Okay, so let's understand what we mean by activity and maybe decay constant. Decay constant. We have talked about radioactivity as being the spontaneous and random disintegration of a heavier unstable nucleus into a stable nucleus accompanied by the emission of alpha, beta, and gamma radiations. However, if if we try to investigate if we try to investigate the decay of a given sample of a radioactive material, experiments have shown that the number of radioactive nuclei in the sample, experiments have shown that the greater the number of radioactive nuclei in a given sample, the greater the decay. If I have 100 nuclei in a given sample, I expect many nuclei to decay as compared to having 20 nuclei in a given sample. So, if for example there are, let's say, n nuclei in a given sample, then after some time we expect that the number of nuclei present is most likely going to be n that was initially present minus delta n, which has just decayed. So let me use a simpler analogy for mathematics. If I have, do I have my pen? Okay. So if at time t I have the number of nuclei present is n, that is starting the experiment or starting the decay, before decay starts, the number of nuclei present is n. And after time delta t, the number of nuclei which has decayed is given by delta n after time delta t. So, I mean, in a time delta t, the number of nuclei which has decayed is delta n. So that means total time is going to be t plus delta t. That is, after time t plus delta t, the number of nuclei which has decayed is delta n, which means the number of nuclei which is remaining after time of t plus delta t is simply going to be n minus delta n. So because we started with n and delta n decayed, that means what remains is actually going to be delta n. But remember, the bigger the value of n, the more the number of nuclei. I mean, the bigger the value of n, the greater the number of nuclei that is going to decay. So it's like there is a relationship between the number of nuclei present in a given sample with there is a relationship between the number of nuclei in a given sample and the number of nuclei which decay in a given time. And that relationship is given by the simpler expression: the number of nuclei decay in a given sample is directly proportional to the number of nuclei present in that particular time. So we shall simply say that in any random process, the rate of radioactive decay, which is dN over the T of a radioactive sample, is directly proportional to the number n of radioactive nuclei present at that time. In other words, the number of nuclei decaying in a given time is directly proportional to the number of nuclei present at that time. We expect that if I have 100 nuclei present in a sample, I expect more nuclei to decay as compared to having 20 nuclei in a sample as my sample. So mathematically, I will simply say negative delta n over delta t is directly proportional to n. Why did I bring in the negative? Because as nuclei decay, the number of nuclei present decreases. So the minus just indicates that the number of nuclei decaying or the number of nuclei present has now reduced. So I'll just simply use that minus to mean that the number of nuclei present or the number of nuclei that remain actually decreases. So if we use a simpler mathematics, just rearranging, so I have the n over the t is equal to negative lambda n. I don't want to do the integration because I know many students don't do maths, but you'll not be asked to integrate this. So separating variables, integrating, for math students, they can really do that. So what is the n over the t? That is the rate of decay. Number of nuclei decaying per unit time. It is later on going to be called the activity. The NDT, the number of nuclei decaying per unit time, is later on going to be called the activity. So you notice that when I remove the proportionality sign, I put equal signs and a constant, which constant I've called lambda. So what does lambda stand for? Lambda stands for the radioactive decay constant, or simply the decay constant. And of course, T is standing for time. So what is this decay constant? What is this decay constant? If we make lambda the subject, of course, lambda would be equal to the n by dt divided by n, ignoring the minus. Lambda will be the n by dt divided by n. Remember, these are the number of nuclei decaying per unit time divided by n, which is the fraction of the total number of atoms or nuclei that decay per unit time. Because when I rearrange this would be the n over n again divided by dt. So this is a fraction of the total number of nuclei that decay over time. That is what we call the decay constant. But note, if any nuclei have decayed, yet the sample was n. So this is the event, the n, and n is the sample space. So the n over n is actually going to be the probability. So this is going to be probability of decay divided by U time. So many times you will simply define decay constant as the probability of decay of nuclei per unit time. Probability of decay of nuclei per unit time. That's what we call decay constant. Probability of decay of nuclei. Nuclei is plural, per unit time. Or you could say the fraction of the total number of nuclei that decay per unit time, which is relatively longer. So because it is the number of nuclei decaying per unit time, and the number has no units, but per unit time that means divided by seconds, the unit of the decay constant is most likely going to be per second. But remember I said the number of nuclei decaying per unit time is later on going to be called the activity. So for those who do mathematics, you can enjoy the next slide, which involves integration. So because the radioactivity, the decay law was stating that the number of nuclei decaying per unit time was directly proportional to the number of nuclei present. We just rearrange. There was a minus here, which means that the number of nuclei remaining decreases. So we could do some integration. I don't want to do the integration. I will just show the integration here for mathematicians, where first of all we separated the variables, and then we integrated from the limit of n naught, where n naught is going to be at t equals to 0, and n is after a certain time t. And we integrated both sides. For the other side, we integrated from 0 to t. Actually, this is dt. So when we integrate and put in the limits, we integrated and putting in the limits, we get ln of n over n naught is equal to negative lambda t. And when you rearrange this, you come up with this expression here. For us, we just need this expression here if we are not mathematicians. No one will ask you to integrate this. So in general, we are saying that n equals to n naught e power negative lambda t. And in the list of constant of formula, many times the equation is going to be stated as x equals to x naught e power negative lambda t. But x can stand for anything. It can stand for activity, where you can write this as a equals to a naught e power negative lambda t. It can stand for the number of undecayed nuclei, where you can write this as n equals to n naught e power negative lambda t. Actually, this is the number of undecayed nuclei. That is the original the number of nuclei which have remained. Then it can also be count rate, where you can write this as c equals to c naught e power negative lambda t. You can use c for count rate. It can also stand for mass, where you can say m is the mass present or which has not decayed, m naught is the initial mass, e power negative lambda t. So in general, you will see this equation in the list of formula. Okay, so that is to understand what we mean by decay constant and how it is related to the number of nuclei present at a given time or after a certain period of time. Okay, so having established that equation, then we should look at a graph. Remember, n is equal to n naught e power negative lambda t, or in general x equals to x naught e power negative lambda t. Of course, you should have some knowledge of using ln. So if I introduce ln, so I have that ln of n is going to be equal to ln of n is going to be equal to ln of n naught. When you introduce ln, when you try to find ln of e to the power of minus lambda t, you will simply get negative lambda t. I think I need to rub off this. I'm not supposed to show this, but it is very important. So this is going to be negative lambda t, because ln is the same as log to base e. So if you get log to base e of e power minus lambda t, the power goes in front, you remain with log of e base e, which is 1. That gives us negative lambda times t. So in other words, we have that ln of n equals to negative lambda t plus ln of n naught. So I'm going to try and compare this with y equals to mx plus c. So when I sketch a graph of ln of n against t, if I sketch a graph of ln of n against t, it is going to be automatically a straight line. Ln of n against it is automatically a straight line, but there is a negative here. There's a negative here. Or you can try to check at t equals to 0, ln of n equals to ln of n naught, which is this point here. And as t increases, because there's a minus here, as t increases, it means the value of ln decreases. That's why the graph is going to the bottom. The graph is going to the bottom. So it is a straight line with a negative gradient. The gradient is negative, and the gradient is, of course, when you compare the equation, the gradient is actually the negative decay constant. So we are saying if we sketch a graph of ln of n against t, because ln of n is equal to negative lambda t plus ln of n naught, I've introduced ln, we have seen that when we compare with y equals to mx plus c, the gradient of the graph is the negative decay constant. So every time we have a graph of ln of n naught against time t, just know that the gradient is the negative decay constant. Even if it is x equals to, even if it is a graph of ln of x against t, the gradient is still going to be the negative decay constant, as simple as that. Okay, so having seen that, let's now try to understand what we mean by activity. Because we have said the number of nuclei decaying over time is directly proportional to the number of nuclei present. So what do we mean by activity? The number of nuclei decaying in a given time is what we call the activity. The number of nuclei, here I say the number of nuclear decays occurring per unit time in the source is what we call activity. It is actually precisely the number of disintegrations. The number of disintegrations a radioactive source undergoes per unit time. So you can define activity as the number of nuclei decaying per unit time, as simple as that. Number of nuclei decaying per unit time, that is activity. Number of nuclei decaying per unit time. So that's what we call activity, or number of nuclear decays per unit time. That is what we call activity. So in other words, because the n by dt is the number of nuclei decaying per unit time, we shall simply say activity is equal to the negative of the n by dt. I say the negative just indicates that the number of nuclei decreases. So activity will therefore be equal to, it will therefore be equal to negative lambda times n, or because we know that n equals to n naught e power negative lambda t, activity can also be negative lambda n naught e power negative lambda t. So in a simple terms, we said activity could also be n naught e power negative lambda t. We saw this from the general equation. What does n naught stand for? N naught would stand for negative lambda n naught. Of course, in the calculation, this minus is going to be ignored. The SI units of activity, we have already said activity is number of nuclei decaying per unit time. And the only quantity with units here is time, which is seconds. So it means it's going to have the same units as the decay constant. So it is going to be per second, or to be specific, it is called the becquerel, in memory of Henry Becquerel. So the SI unit of activity is the becquerel, which is written as BQ, but it is simply equal to per second. It is simply per second because it is the number of nuclei decaying per unit time. That is the activity. But remember, I said in the calculation we shall simply use In calculation, many times we shall use activity as being equal to lambda times n. We shall ignore the minus. So if I want initial activity, I would say initial activity is equal to lambda times initial number of nuclei present at that time. So that is what we call activity. The units are going to be the becquerels, or it would be per second. So other units that you'll find per hour, you'll find per year, and you'll find per day are being used as units of activity. Okay, so since we have established that the equation which relates number of nuclei present to time is actually n equals to n naught e power negative lambda, which is an exponential equation. Therefore, it means we can predict that any graph for the equation x equals to x naught e power negative lambda t is always going to be exponential. So if I try to sketch a graph of activity against time, it is going to be exponential. Remember, it is different from ln. ln is going to be a straight line with a negative gradient. But if it is just x against t, it is going to be exponential. N against t, it is going to be exponential. Count rate against t, it is going to be exponential. So this can be illustrated in this slide here. So graphical representation, we shall represent activity with time as an exponential curve. Remember, I'm saying this could also be n, number of nuclei present against time. This could be mass against time. This could be anything against time. As long as it is not ln, it will be an exponential curve, because remember, we have just established that activity is equal to a naught e power negative lambda t. This is an exponential equation. At t equals to 0, a is going to be equal to a naught at t equals to 0. And as t increases, a is going to decrease exponentially, because this is an exponential equation. So the graph looks like that. And what I'm saying is that all radioactive decay graphs are going to have the same characteristic shape like this one here. All radioactive decay graphs are going to have the same characteristic shape like this one here. So the graph will always be like that. And you saw this graph in IGCSE, in your nuclear physics of IGCSE. Okay. Then from this graph, I want us to establish something very beautiful. Instead of activity, I've now used a number of nuclei present, that is n, against time. Remember, from the equation n equals to n naught e power negative lambda t, whenever t equals to 0, n is equal to n naught. That's why the graph starts from here. So I want us to note something, that after a certain time, which we are going to later on call the half-life, the number of nuclei present is half the original number. After a certain time, which we are later on going to call the half-life, the number of nuclei present is half the original number. And experiments have shown that after an equal amount of time again, what was a half will again reduce into another half. That is, it becomes a quarter of the original. And the time interval is exactly the same. After a further half, the number of nuclei again divides by 2. So what is actually happening here? Let's use a simpler table here to understand this. At time t equals to 0, the number of nuclei present is n naught, which means n is equal to n naught, and we can mathematically introduce a half power 0, because we know that anything to power 0 is equal to anything to power 0 is equal to 1. So if n is equal to n naught, I could simply say n is equal to a half power 0 times n naught, which still gives me n equals to n naught. So how many nuclei have disintegrated? Nothing. That's why I said n naught minus n naught equals to 0, because present was n naught, and what is initially it was n naught, and what is present after t equals to 0, it is n naught. But then after one half-life, after time which is equal to half-life, the number of nuclei present divides by 2 or reduces to half. And if I bring in the half here, it is the same as having 1 over 2 to the power 1. A half n naught is the same as 1 over 2 to the power 1 times n naught. So what is the number of nuclei that has disintegrated? So I will get the original, which is n naught minus a half n naught, which gives me a half n naught. After another half-life, that is, we have two half-lives. Again, what was n naught over 2 reduces by half, so it becomes n naught over 4. But note that a quarter of n naught is the same as a half squared, then times n naught. So what has reduced? What remains is a quarter of n naught. So what has disintegrated will be the original minus what has remained. So 3/4 have disintegrated. And after a further another half-life, again what was a quarter n naught becomes 1 over 8 because it goes on reducing by a factor of a half. So it becomes a 1 over 8 n naught. But remember, 1 over 8 is the same as a half power 3. So I can write 1 over 8 n naught as I can write 1 over 8 n naught as 1 over 2 power 3, then times n naught. So if a half or 1 over 8 n naught has remained, it means what has decayed is automatically 7 over 8 n naught. What am I trying to arrive at? So look at this number and the power of a half. So this number here is going to be called n. This number here, 0, 1, 2, 3, is going to be called n. And so in general, I will simply say that n, the number of nuclei which remain, or the number of nuclei after a certain time, is going to be given as a half power n, then times n naught. But what is n? For example, you have seen 3 half-life equals to n. I mean 3 half-lives. N was 3. So n is going to be small n is going to be called the number of half-lives, which is going to be the total time divided by t half. So small n is going to be the number of half-lives, which is going to be total time over the half-life. So in general, or in calculation, sometimes we may be forced to use a simple equation such as n equals to a half power n times n naught, where small n is the number of half-lives in a given time, as we shall see in calculations. Okay, so let's now define what we call half-life. Since we have now been dividing by 2 after a certain time, so we should now define what we call half-life. What we call the half-life of a radioactive nuclei is the time taken for the number of undecayed nuclei to be reduced to half its original number. The number of undecayed becomes half the original, that is half-life. Or it's the time taken for the activity of a given sample to reduce to half. Remember, the number of nuclei decaying per unit time is directly proportional to the number of nuclei present. So it means if the number of nuclei present has reduced to half, it means also the number of nuclei decaying per unit time is most likely going to be half. That's why we are saying it's the time taken for the activity of a given sample to reduce to half the original activity. That's what we are going to call the half-life. The time taken for it's the time taken for the activity of a sample to reduce to half the original activity. So remember, we have already derived that n equals to n naught e power negative lambda t. But remember, we have already been seeing that at half-life, n becomes half of the original. So if n naught is the original, then after half-life, n becomes half of the original. Therefore, whenever t is equal to half-life, when I write t subscript half, it is half-life. Whenever t is half-life, the number of nuclei which remains is half of the original. So what does the first equation becomes? So substituting those conditions, if I put t a half in the first equation and I put n naught over 2 in the first equation, I have that where there is n, I'm putting half n naught. equals to n naught e power negative. Where there is t, I'm putting half-life, so n naught has cancelled out. So I remain with a half equaling to e power negative lambda t a half. Now I take logarithms both sides, or I introduce natural logarithms. So if I introduce natural log on the left-hand side, ln over half equals to ln of e. Remember, whenever you take ln of e, you only remain with the power. So I remain with ln of half equaling to negative lambda t a half. When I split the ln, because this is logarithms, division is subtraction, so I have ln of 1 minus ln of 2. On the left-hand side, I have only negative lambda t a half. So, of course, ln of 1 is 0, so I will say 0 equals to 0 minus, not equals to. Ln of 1 is 0, so I'll say 0 minus ln of 2 equals to negative lambda t a half. So the negative cancels out. So I'm now remaining with ln of 2 being equal to lambda times t a half. This a half is a subscript, it's not t times a half. So if you make lambda the subject, you can find an expression for the decay constant. Or if you make t a half the subject, you find that t a half is the same as ln of 2 divided by ln of 2 divided by decay constant, or you'll find out that t a half is the same as, of course, ln of 2 is 0.693 divided by the decay constant. So sometimes you'll find that expression, sometimes you'll find that expression there. So in general, I'm saying that the half-life is given by ln of 2 over lambda, or the half-life is given by 0.693 over lambda, where lambda is the decay constant. You should be able to derive this equation for 3 marks. You should be able to derive that equation for 3 marks. Sometimes it is the decay constant which is made the subject. So whichever is made the subject, you should be able to derive it. Okay. So is it possible for us to derive n equals to a half, n equals to a half, n power n times n naught without using the graph? Of course, we can do that. Remember, n equals n naught e power negative lambda t, and then lambda is ln of 2 over t a half. We have already seen that from the previous slide. So from n equals to n naught e power negative lambda t, and from what we have already seen, that half-life was ln of 2 over lambda, making lambda the subject. I'm just going to substitute this in this equation. So n over n naught, I've just divided equals to e power negative lambda t. Where there is lambda, I have put ln of 2 over t a half. When I rearrange, I have e power t over t a half times ln of half. Remember, n, small n is the number of half-lives, so this one here, this quantity here, is going to become small n, which is going to be the number of half-lives. If I have 100 years and the half-life is 10, the number of half-lives in 100 years is going to be 100 divided by 10, which will still be 10. So n will be 10. So n is the number of half-lives. So this is going to simplify. This is going to simplify to where there is t over t a half. I have put there n over half. Then I use mathematics to take n backwards. So it becomes a power. The rules, logarithmic rules are very important here. So n has moved backwards, so it becomes power a half. And if you have e raised to power of the ln, remember ln is log to base e. So when I raise e to the power of ln, I only remain with the power. So this means n is going to be equal to n naught. I mean, n over n naught is going to be a half power n. If you are not a mathematician, you may be asking how does this become just a half power n? Let's say y equals to e power ln of a half to the power of n. Then I introduce ln again on both sides. So on the left hand side, I have ln of y equaling to ln of e, which is raised to the power of ln of a half to the power of n. But of course, I've already said when you get ln is log, ln of e is the same as log of e to base e, which is 1. So I only remain with the power. So it means I'll have ln of y being equal to ln of a half raised to power n. So I cancel out the ln. So it means y is equivalent to just a half to the power of n. This is a by the way. For mathematicians, you should be knowing that. So that's how I came up with n over n naught equaling to a half to the power of n. So in general, what I'm saying is that in general, the number of radioactive nuclei that remains after decay is given by n equaling to n naught. I mean, n equals to a half power n times n naught. So in calculations, we shall also use that equation many times. In calculations, you may also borrow that equation many times. I have listed a few half-lives of some materials, but you don't need to remember them anyway. Uranium, it is about 4,500 million years. That's why it is very dangerous if it undergoes if it is in the environment and is not properly handled. Uranium remains radioactive for almost 4,500 million years. Then we have radium. Radium, 1,600 years. We have polonium, 138 days. We have lead, about 27 minutes. We have radon, which is about 1 minute, and many others. I couldn't list all of them, but these are some of the materials whose half-lives you may need in the future to talk about when you continue with your further studies. Let's do a few examples. Before we do examples, I want you to think about all the expressions or the formulas that we have just derived. Because if you have all those formulas, then solving the examples becomes very easy. Number one, we have already said ignoring the negative, activity is equal to the n by dt. That's number one. Number two, we have also seen that n could be equal to n naught e power negative lambda t. We have said activity is equal to lambda n, ignoring the negative. We have also said t a half could be equal to ln of 2 divided by the decay constant, or whichever you make the subject. We have also seen that n could be equal to a half power n times n naught, where small n is equal to t divided by t a half. If I have these equations, it means I'm done with radioactivity calculations because the calculations require n of those. In general, remember x is equal to x naught e power negative lambda t. That means we could use it for activity, we could use it for mass, we could use it for count rate, and so on and so forth. So from these equations, I can solve any equation in radioactivity. Number one, the half-life of radium is 1.62 times 10 to the power of 3 years. What fraction of radium would remain after 1.0 times 10 to the power of 3 years? So I'll choose the simplest. N equals to n naught into a half raised to the power of n. That is the simplest. So the number of nuclei present equals to half original number times a half to the power of n. Remember, n is equal to t divided by t a half. So the half-life or the total time is 1.0 times 10 to the power of 3. I don't know whether this is correct. Divided by the half-life, which is 1.62 times 10 to the power of 3. So this one has cancelled. So n is going to be n is 1 divided by 1.62. I'll not divide that. I'll just take the fraction. So we want, this is the number of radium which remains. This is the original. So the fraction is going to be n divided by n naught, which is going to be a half power n, which power is 1 over 1.62. So I'll just use, this is a power. So I'll just press my calculator. 0.5 to the power of so this is giving me a fraction of 0.652. I can check it. 0.5 power 1 divided by 1.62. Yeah, it is 0.652. Okay, so I use the shortest method. You could also choose to use a different method, but I think this is the shortest I could afford. Okay, so let's check, maybe there is an answer. Okay, the answer is 0.652 as we have seen. Example number 2. Radioactive cesium-137 has a half-life of 30 years if the initial number of cesium nuclei is 10 to the power of 4, so that is n naught. What is the number of cesium nuclei that have decayed after 90 years? So we shall first find what remains, then we shall subtract to get what has decayed. Okay, so let's try to calculate this. Since I have the half-life and I have the time, this is half-life, t a half, and we have t as 90, so it means the number of half-lives in 90 years is going to be 90 divided by 30, which gives us 3 half-lives. Then the number of nuclei present could be equal to a half power n times the original number of nuclei. So the number of nuclei which remains is a half power 3 times the original number, which was 10 to the power of 4. So I'll just press my calculator. That is 10 divided by 8. What is that? Exponent 4 divided by 8. So the number of nuclei which remains is 1250. So this is the number of nuclei present after that time of 90 years. But we want the number that has decayed. We want delta n, the number which has decayed, which is n naught minus n, which is going to be 10 to the power of 4 minus 1250. And I think this is 8 because this is 10,000. So this is 8,750. So the answer is 8,750. So that is the number which remains. Okay. Then let's check example number 3. A radioactive sample is known to emit alpha, beta, and gamma radiations. Suggest 4 reasons why the count rate measured by the Geiger counter placed next to the sample would be lower than or higher than the activity of the sample. I think with this one we have discussed this in the lesson. I'll just list them out here. Number one, we talked about background radiation. These are commonly from cosmic rays arriving from the atmosphere or from underground. We mentioned that the gamma rays are not always detected because they are weakly ionizing. We mentioned that some radiations are absorbed within the sample. That's what we call self-absorption. We mentioned that the detector is unidirectional, which means if the particles emitted are not towards the detector, then they are not going to be detected. So the count rate is not going to be registered. So the detector is unidirectional. We also mentioned that the daughter nuclei could be radioactive. Therefore, it also emits other particles, which could make the activity to be higher. And lastly, we mentioned that the count rate could be inefficient, or it could have experienced what we call dead time. At some point, it failed to work. So the time of the counter affects the activity. Okay, I think the next thing is students should be able to solve. So you can pause the video at this point and you start practicing. I've given hints where possible. Number one, radioactive source emits beta particles. It has an activity of 2.8 times 10 to the power of 7 BQ. Estimate the number of beta particles emitted in a time interval of 2.0 minutes. State one assumption made. Okay, so you can always pause the video. You can always pause the video and try to solve these questions. I will not go through them, but I've tried to give you some of the answers which most of my students give me every time. For example, for question number one, I expect you to get an answer which is most likely going to be Look at me sometimes like all you want to I expect you to get an answer which is 3.4 times 10 to the power of 10, power 9. Of course, for question number one, I expect you to use dN by dt. You must have all the formulas at your fingertips to be able to solve these questions. So I will not read through all of them, but you can read through the question, pause the video, read through the question, and try to see if you can get the answer. So for question number two, I expect you to get this answer here. Question number three, I expect you to get that answer. For question number four, you can try to see this answer here. For question number five, I expect you to get this answer here. I've given you a hint. Question number six, A and B, I've given you a hint. I expect to get those answers. For question number seven, you can get a graph paper and try to sketch that graph. Of course, we know that this is if it is a graph of n against t, it is going to be an exponential curve. I gave you a hint where I calculated the values of n at intervals of 1.0 minutes. So you can try and see if you can sketch that graph on a graph paper. For question number 8, I expect you to get these answers. Of course, question number 8 is going to be one of the most challenging questions, but I expect you to get these answers. If you notice that the answer is different from what you get, maybe there is a problem. I can always check because these answers were obtained by my former students. So I always don't solve these questions, students solve them. For question number 9, I expect you to get this answer here. For question number 10, we have derived this equation, I think. we have derived this. You just refer to the notes where we got n equals to n naught e power negative lambda t. F is n over n naught. This is F, which is e power negative lambda t. Remember, lambda is ln of 2 over half-life. And remember, t over half-life is t over t a half is small letter n. Small letter n is t over t a half. So you should be able to substitute and arrive at this equation here. For question number 11, you can just complete the table. At t equals to 0, n is equal to n naught of 400. So this is going to be n naught. So using the equation n equals to n naught e power negative lambda t, I expect you to complete this table here, and then you should be able to draw a graph. So you can round off to either two significant figures. I think two significant figures will be fine for easy plotting of the graph. So we're going to draw a graph of n against t, so it is going to be an exponential curve. Then for question number 12, I expect you to just use one of the formulas to get this answer. One of the formulas to give you this for part B, you should be able to use, for question number 12, they say the decay constant, the sample phosphorus contains that number of nuclei, the decay constant is that. Calculate the number of undecayed phosphorus, 32, in the sample after 10 days, 20 days, and 40 days. So this is a continuation of question 13. So I expect you to get n of these, to get these answers for 10 days, 20 days, and 40 days. For question 15, you just use one of the equations or one of the formulas and obtain that answer. For question 16, I expect you to use one of the formulas to obtain those answers. For question 17, I expect you to use one of the formulas to obtain these answers. For question 18, calculate the fraction of the sample of uranium remaining undecayed. So that means you first get what, okay, this one is direct, you just use n of the formulas. I will not tell you which one, but remember I say the simplest formula is n equals to a half power n times n naught, where n is number of half-lives, which will be 114.4 divided by 4.8, and you'll get n, which is the number remaining. For 19, I expect you to get this formula, these answers, A for part B, for part C, for part D. The answers, if you don't get the same answers, then you just write a message and maybe I can help you. So the half-lives have been given in this table. So we just refer to the table and we find what is required. Of course, the simplest formula to use is n equals to a half power n times n naught. That is the easiest formula to use. Then for question number 20, the half-life of radioactive substance is 24 days. Calculate the mass of a substance which decayed after 72 days. If the original mass is 0.64. So I say the simplest formula, I'll use m equals to m naught into a half power n, where n is going to be 72 divided by 24, the number of half-lives. I think 72 divided by 24 is 3. So this is going to be, the mass which remains is going to be 0.64 times a half to the power of 3. Calculate the mass of the substance which decayed after. So this one is what remains. Then after getting what remains, then if you want the mass which decayed after 72 days, you just subtract m naught minus the value of m. So you first calculate m here, then you subtract from 0.64. You should be able to get that. You can use any other formula that you want. The half-life of a sample is 14 days. The initial mass is 52. Starting with 52 grams, the final mass is 2 grams. You can still use the same formula. M is equal to m naught into half power n, because we want to calculate T. If I finish getting n, initial is 52. Sorry, initial is 2. Original is 52. And then I get a half power n. Of course, here you will have to introduce some logarithms. If you can't do that, then use m equals to something is wrong here. You can use m equals to m naught e power negative lambda times t, because we want to calculate how long it takes. You have m is 2, m naught is 52. You have the half-life. You will get the decay constant from ln of 2 divided by t half. So you'll be able to get the time. For question number 22, I think that is direct. You should be able to get that answer for part 1 and for part 2. For question number 23, I think this is direct. You just choose one of the formulas to be able to get that. Percentage that has decayed, you first get the number of nuclei which has decayed, which is n naught minus n. Then you divide by n naught, of course. So in other words, we get the n over n naught then times 100 to get the percentage that has decayed. So you should be able to get these answers. 24, I think 24 is also direct. You should be able to get the answers given at the bottom here. I think 25 is also direct. You should be able to get the answer given here. 26 is also direct. You should be able to get that answer. 27 may not be direct, but you should also be able to manipulate it to arrive at that answer. 28 is direct. They have given you activity as 10 becquerels. The activity of a dead sample of wood is 10 becquerels, while the activity of a living plant from the same species is 19. So this is original, A naught. This is after a certain time. So I'll just use A equals to A naught e power negative lambda t. If you want, you can use A equals to a half to the power of n times A naught if you are good at math. So you can get n. When you have n, remember n is equal to t over half-life. Then you should be able to get t. T will be the age of the wood. If you are using the first equation, remember decay constant is ln of 2 over t a half. If you use the first equation, decay constant is ln of 2 over t a half. So you should be able to arrive at approximately 5,000. Of course, in an exam, you're supposed to write these to two significant figures. So this will be 5200 years. Then 29, a certain instant, a piece of radioactive material contains 10 power 12 atoms. The half-life of the material is 30 days. Calculate the number of disintegrations in the first second. So that is the activity. The number of disintegrations in 1 second. So this is number of nuclei present, and this is the half-life. If you want, you could use activity is equal to lambda times n. Calculate the number of disintegrations in the first second. So lambda can be got from lambda equals to ln of 2 over half-life. Then n, you could use 10 to the power of 12. So capture the number of disintegrations in the first second, or you could use A, because number of disintegrations is actually activity. Activity is equal to the N by the T. So if you can find the N, which is the number of nuclei which has decayed, of course divide by T, which time is 1 second. So that means you need to find the N. Alternatively, you could use A equals to A naught e power negative lambda times T. Remember, T is going to be 1. That is in the first second, so T is 1. But the K constant is ln of 2 over T half. Then you substitute and you'll be able to get, but of course, A naught is this. A naught will be lambda times N naught. So you should be able to get the activity there. Then radioactive cesium has half-life of 30 years. Initial number is 10 to the power of 4. What is the number of cesium that has decayed after 90 years? I think I have solved this in one of the examples. So the answer is 8750. This was example number 2, I think. I think that is all.
Myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set the rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Something from nothing. I sit here looking for an answer.